Good evening, everyone. And so I'm going to talk a little bit today about the Rescience journals. And Nicolas Rougier, who is one of my advisors, has been the founding member of both of these journals that I will talk about. And he's based here at IMN. So first, going back to why did they decide to start these journals? Because, of course, as we know, there's a replication crisis in science. Crisis being a heavy word, but it's very well known in academia. Particularly with regards to replicability. And you would think that in computational and computer sciences, at least, this problem would be lesser, owing to because the resources used in terms of data, in terms of software, a lot of these are available. And you would think that more computer science papers, at least, would be reproducible papers. But there was, in fact, a study done in 2016 by these two authors, and they found out that out of a pool of 515 potentially reproducible papers that they looked at, they were only able to successfully run the code of 102 of them, so less than 20%. And this is not even going into whether they were able to replicate the results or not, but just out of the box whether they were able to run the code or not. So it's clearly a huge problem. Fun story that when I tried to look at the original paper, of course, it was behind a paywall, which is a bit ironic. But so another reason for non-replicability is that clearly in most prominent journals, there's a publication bias for originality in the research world and academia in general. With regards to reproducibility, now that there has been a lot of focus on this in the past couple of years, journals are trying to make steps to make work more reproducible. And so PLOS ONE and eLife have taken out some statements owing to the sharing and availability of materials, the software and the code, but we're still very far from where we'd like to be. So this was the motivation and the backdrop behind which Nicolas and a colleague of his, Konrad Hinsen, decided to start the Rescience journal in September 2015. So initially it was just called Rescience, but recently it has been renamed Rescience C because they started another journal, Rescience X, because Rescience C is purely focused on computational work, whereas Rescience X is now focused on experimental work. And both of these exist, and they are free to publish in and free to read. So a fun thing that they did a little while ago was they conducted a workshop or a challenge in 2020, where the idea was that you take any published, your own published work. The only condition was that it had to be published before 2010, and they wanted to check if you could run the code and produce the same results that you had then. And again, just to highlight that this is not a trivial problem, even if you have all the benchmarks, all the code available, just owing to whether the softwares have changed, if the dependencies were not locked correctly, it can lead to quite a lot of problems. And in the original publication where they introduced this journal, they've actually cited a lot of other references where people tried to do this and ran into problems, even when everything was supposedly correct according to the guidelines we are usually given. So when we start talking about reproducibility, and we talk about that a lot in this journal club, right, is just what the taxonomy of these terms and what they mean. Again, someone has written an entire opinion article on this about a brief history of this confused terminology. So owing to that, it's important to clarify with respect to these journals, what they mean by reproducing and what they mean by replicating. So reproducing for them is running the same software on the same input data as the original publication and obtaining the same results, with the goal to verify that the computational protocol that was published in the paper was recorded correctly. So all the information with particular regards to the methods that you would need to obtain the results is there in the original publication. Whereas replicating is a much stronger quality indicator because it means repeating the published protocol, but you could vary the technical details. Keeping in spirit of the intentions of the original paper, keeping that aside, the other technical details which should not have an impact on your results. So for example, with regards to computational publications, using a different software or changing the initial conditions, these should not affect the results that you get. And with the eventual goal to show that independent implementations done by different teams can generate equivalent results. Again, saying equivalent with the caveat that this could mean different things in different domains according to different experts. So this is open to interpretability, but still broadly, this is the definitions they use of reproducible and replicable science in these two journals. with the overarching goal of creating papers and creating work that is reproducible. Okay, I'm getting good.
Reproducible.
No, it's okay. Never mind. Moving on. So one question, of course, that comes up is why replicate? Why do we replicate? Why is the need for such journals? As we already discussed, that most journals they have a heavy bias towards publishing original research. In fact, now they've done. There are some journals in psychology which, even though they explicitly cite that we are open to receiving work that has been replicated, only 3% of all the contributions, all the papers that are even submitted, are papers which are being replicated. Whereas this is not, you think that this is something we don't do in our regular work, which is not true at all. When we start off as students, most master students, even as PhD students, we reproduce and try to replicate a lot of code just to become familiar with the specific scientific domain that we're working in. So particularly for students, it's something we do all the time. Whereas even senior researchers sometimes will have a critical need for a specific piece of code that they want to either build on, so improve a model, or sometimes they also want to compare a model to something that they're already doing, and a benchmark for this is very necessary. Also, a lot of times we end up spending quite a lot of time on replicating results. Again, even in most cases, actually, the data or the source code is just not publicly available. But even when it is, even in 2 years, a lot of the dependencies and so many things can change, and it would take you significant time. Sometimes there was another research done where they took 3 months in trying to just replicate a code that was already publicly available and published. And in fact, it's a bit of a hassle because a lot of papers will even say that code or data is available upon request of the authors. But if this paper has been published like 5 or 6 years ago, the email has changed, people have moved across disciplines, and you just cannot contact them anymore. So once, say, you have replicated something, which we all are obviously all doing, where is the space to have a publication for these results that we're replicating? And hence, Rescience C and Rescience X come into the picture. And these are just all the practical difficulties that I've been talking about, not even going to the domain of what we already know, that replicating science is extremely important for scientific progress and research and progress in general. So specifically, the publication criteria for these two journals is pretty straightforward. The reference to the work being replicated needs to be mentioned, so the precise reference. An explanation of why the authors think they were able to replicate the paper. So either they found the same figures or graphics, they found the same behavior or whatever. Or in case they have failed, the reasonable justification for why they think they have failed. And this especially is an very important part because to be able to track down why the replication failed, was it a matter of interpretation? Was it a matter of not precisely recording the details and so on? A description of the difficulties that they faced while trying to replicate the paper. Of course, the open source code, all of this is hosted on GitHub. So it requires just creating a pull request when you're trying to submit a paper. And very, very importantly, an explanation of the code. So all the README that we typically have of how to run the code, what are the dependencies that you need, and so on. Just to have a little break in between, even if you do all this, even if you publish your code, you do all of this, it's again, like there are some good practices and it's not always so simple. So I found a couple of good comics to describe the problems we all face. So the summary of this being just clear code is extremely important if you want other people to use it. When you write dependencies, try covering all the bases. And finally, yes, of course, in trying to create a standard that encompasses everything, you might end up creating yet another new standard. And who has the need for that? Okay. Back to focus. Based on, and this is from one of the papers that the authors of these journals published 3 years after they had started the journal, so when it was still relatively new, and it was the initial things that they kind of took away. They noticed a certain pattern. So while reproducibility is and the reasons for non-reproducibility are different depending on the domain. Some key things that they found, the commonalities that they found was that for short-term reproducibility, at least, standard problems were either missing code and data, undocumented dependencies, or inaccurate or imprecise descriptions. Whereas the effort of Rescience is still laudable because of its impact in long-term reproducibility. So it might be that even a code that you publish in Rescience is unusable after 2 or 3 years because of the software has changed and so on. But what helps is the article that you have submitted, which is logging all of these difficulties, so which is kind of branding the original research as something that is reproducible and replicable. And this helps in creating a complete and consistent description of the model at hand. And finally, they found the open reviewing system that they have in Rescience extremely helpful, because all the reviews are there for everyone to see, and everyone, not just in the domain of academia, but absolutely anyone can go and comment on it and ask questions and so on. So it's a much more transparent system than what we are used to seeing in academia. This is something that has been spoken about in this journal club earlier, but to keep it brief, going forward, since we spoke about successful replication a lot, and of course, Rescience has a bias for successful replication, justifiably so, because if you claim that you have failed to replicate a study, it's a pretty heavy claim, and there needs to be due process in it, a much more thorough investigation of the code, of the interpretation of the code and the description and so on. And so far, Rescience has a model of handling this, but this is what they want to achieve going forward is a model of cosign, where even before publication of a paper, it is verified as reproducible by another group of authors. And like this helps certification of work as reproducible. Finally, just a few stats about Rescience. So far, in their 7 years of running, they have published 162 articles. There's a community of over 125 voluntary reviewers. It's completely open source, so it's completely hosted on GitHub and Zenodo. Of course, the code needs to be open source. The most popular languages are Python and R. And mostly right now, they have received submissions in the domains of computational neuroscience, neuroimaging, computational ecology, and computer graphics. And typically, the review process, it's really short. It would take an average of 100 days with an average of 50 comments back and forth in trying to improve the publication. And finally, you're good to go and you're in press. Just a quick note on some other not related efforts around this. So particularly in the effort of educational science, there's this effort called the Carpentaries, which they teach foundational coding and data science to researchers worldwide. Then there are these two efforts, SkyUnit and OSV model validation, which helps in automated validation of scientific models. And finally, there's another really interesting one called software heritage, which is aiming to catalog all the publicly available software that's out there. So to deal with the software dependencies that we were speaking about earlier. So software is cultural heritage, basically.